Alright, in this video I'm going to look at a couple more examples of finding the derivative of our natural log. And with the examples we're going to look at here, I'm going to show you two different ways we can solve the same problem. So we have a function, the natural log of x multiplied by x squared plus 3, and that whole quantity is cubed. And we're taking the natural log of this whole piece. I want to look at how we can use our logarithmic properties to rewrite this first. And if you recall, if we're going to rewrite this, multiplication, we can split the multiplication up into addition, where I could take the natural log of x plus the natural log of x squared plus 3 cubed. Okay, so that's one of our logarithmic properties. And then we could go a step further if we would like. And we could think of this as the exponent 3. Remember the property there, we can pull the exponent out front and make this 3 times the natural log of x squared plus 3. So here, after we rewrite this problem, now this is set up very easily in order to take the derivative. We have the derivative of the natural log of x, which would be du over u, so that's simply 1 over x, plus we have 3, that's our constant multiplier, and if we take the derivative of ln of x squared plus 3, we take the derivative of x squared, which is 2x, and 3 goes to 0, and that's all over the u, which is x squared plus 3. And there we have our derivative, and we can simplify this a little bit by multiplying by the 3. So we would have 3 times 2 would be a positive 6x over x squared plus 3. And that's our derivative. Now you could get a common denominator and we could add those together, but this is sufficient for the derivative. Now I want to look at an alternate method. I think this is much easier using the logarithmic properties. However, if we didn't use the properties, how could we take the derivative of this same problem without rewriting it first? Well, if we do that, if you notice now, the natural log of x squared plus 3 cubed, we have to take the derivative of u. Well, all of this inside the brackets would be our u. Because this is multiplied, we're going to have to use the product rule. So we would take our first term multiplied by the derivative of x squared plus 3 cubed. Well, as we take the derivative here, we're going to have to use the chain rule. So you can see here, this is getting really involved with the product rule and the chain rule. So the logarithm properties made this much easier. So the chain rule says we're going to pull the 3 out front, and then we would have x squared plus 3. And then by the chain rule, we have, and that would be x squared plus 3 squared. And by the chain rule, we have to take the derivative of the inside, x squared plus 3, which becomes 2x. And then it's plus our second term, which is x squared plus 3 cubed, multiplied by the derivative of the first, which is the derivative of x, which is simply 1. Now, that's our du. That's the derivative of u, but remember, all of that now is divided by u. Well, our u is x times x squared plus 3 cubed. So if we now simplify this, this is our derivative. Is it going to match up what we found over here on the left? Well, we have x times 3 times 2x, so that's going to be 6x squared. And x squared plus 3 squared. Now I'm going to go ahead and split this up. This is our common denominator, so I'm going to write this over x times x squared plus 3 cubed. And then we have the second part of the numerator, which would just simply be x squared plus 3 quantity cubed. And of course, that would all be over the common denominator as well. So now if we simplify, 6x squared over x, the x is going to cancel there, so we'll be left with 6x, and then of course the x squared plus 3 squared on top would cancel out 2 of the x squared plus 3's on the bottom, so you're left with simply x squared plus 3 on the bottom. And then over here, the x squared plus 3's cubes will cancel, and you're left with 1 over x. And if we look closely, this is the same derivative that we found over here on the left. So either way you want to work this is fine. I really think the derivative is a lot easier if you use the logarithm properties to rewrite it. If you prefer, you can practice here with the product rule. And remember, inside the product rule, we had to use the chain rule. All right, the next example I have is the natural log of 2x over x plus 3. And we want to find the derivative. And just like before, I want to use our logarithmic properties to rewrite this first. And we know that if we're dividing, we can rewrite the function simply as division becomes subtraction. So we could write this as ln of 2x minus the ln of x plus 3. And now we can simply take the derivative of each piece. Natural log of 2x, the derivative is our u is 2x, so the derivative would be 2 over 2x minus the derivative of our u here, x plus 3, is simply 1 over x plus 3. And there's our derivative. We could certainly simplify this to 2's cancel, 1 over x minus 1 over x plus 3. And if you preferred here, again, this is your derivative. You could go a step further and come up with a common denominator. If we did so, our common denominator would be x times x plus 3. So that means we need to multiply the 1 by x plus 3. And over here, we would have to multiply the 1 by an x. So we would end up with x plus 3 minus x. So therefore, the x's would cancel, and we would have 3 over x times x plus 3. So there's an example. If you want to get a common denominator, we could do so. Now, what would happen, just like the example before, if we decided to take the derivative in the form that it's in? Instead of using the logarithm properties to rewrite this as ln of 2x minus ln of x plus 3, if we take the derivative in this form, we have to realize that the 2x over x plus 3, all of this is our u. So we need to take the derivative of that, which is going to require the quotient rule. So the quotient rule says we're going to take the bottom piece, x plus 3, multiplied by the derivative of the top, which would be 2, minus the top piece, the 2x, multiplied by the derivative of the bottom, which would simply be 1. And all of this is over the denominator, x plus 3 squared. So there's the derivative. All of this is du. But now for the derivative of the logarithm, remember this natural log, all of this is still divided by u. Well, our u is the 2x over x plus 3. So remember, if we want to simplify this, then on top, we could go ahead and distribute the 2. If we distribute the 2 up here, we're going to get 2x plus 6 minus 2x over x plus 3 squared. Okay. Now, at this point, what I'm going to do is I'm going to take the denominator here, this 2x over x plus 3. If we're dividing fractions, remember, that means we're going to multiply by the reciprocal. So the reciprocal of this then would be x plus 3 over 2x. Okay, so that'll make the simplification a little bit easier. So now we have 2x minus 2x, so we're left with 6 over x plus 3 squared. And this is still going to be multiplied by the x plus 3 over 2x. And at this point, we can see that the 6 and the 2x, or the 6 and the 2 rather, 6 divided by 2, that would give us a 3 on top. The x plus 3 on top will cancel one of the x plus 3's on the bottom, so we'll still be left with x plus 3, and then we still have the x. So notice once again, we have the exact same answer as before. And I guess depending on whether you like to use the quotient rule or not, but I think you'll find that simplifying this to your logarithmic properties here is going to make the derivative a lot easier to calculate. All right, there's one last example I want to look at in this video, and that is if we have y equals the natural log of the square root 2 plus cosine squared x. Once again here, we could use our logarithmic properties to rewrite this. We could think of this as y equals, this is the square root, so we could think of this as the natural log of 2 plus cosine squared x. Instead of the square root, we could think of that to the 1/2 power. And if we think of raised to the 1/2, we could leave it this way and take the derivative to get du over u, but that's going to require us here to use the chain rule. And that's perfectly fine. Or we can get around that by pulling the 1/2 out front of the natural log, and then we're just left with the natural log of 2 plus cosine squared x. So that makes things a little bit easier for us. So we could have y prime then, if we take the derivative, bring down our 1/2, that's going to be our constant multiplier. So now if we take the derivative of u, the derivative of 2 is 0, and we have cosine squared. Now here we're going to think of this maybe as cosine x. This is the whole quantity squared, remember. So really here we're going to have to use that chain rule as well. So we're going to pull the 2 out front. Okay, so the power comes out front, so that's going to give us 2 cosine x, and the power goes down to a 1. Now we have to take the derivative of the inside part. We need to take the derivative of the cosine function, and the derivative of cosine is negative sine x. All right, so that's du. Now remember though, we have to take and divide all of that by u, and our u is 2 plus cosine squared x. Okay, so keep in mind this is du over u. So then if we simplify this, we can take our 2 here, the 1/2 out front is going to cancel the 2 here because this is strictly multiplied on top, so we can certainly just cancel that out. So then on the top we have a negative cosine sine of x. And on the bottom we're left with 2 plus cosine squared. And that is our derivative. So hopefully again here, with taking the derivatives of natural log, I'm hoping that you will find this to be somewhat straightforward, but just be careful whether you have to possibly use the chain rule, or is it a lot easier to find the derivative if you use these logarithmic properties to write it as addition if you have multiplication, or if we are dealing with division, we could rewrite that as subtraction.